4. Oscillations. Introduction. The purpose of this lab was to observe the motion of a mass connected to a spring. The main physics principles we are observing here are oscillation and energy systems. Models. Here we can see that for both the x and y position graphs that the models and experiment, though a little off, display the main principle at hand here, which is their oscillation. Both the models and experiment in both cases have consistent waves of the period, and both have consistent amplitudes even though the amplitudes between the model and actual are different. In the energy graph, we can see the changes in kinetic energy, potential energy of gravity, potential energy of the spring, and the total energy. System and surroundings. The system includes weight and spring, and the surroundings include the professor that dropped the weight and gravity. Initial conditions. The weight had a mass of 0.042 kilograms, which was a constant in the experiment. The K, the stiffness of the spring, was also a constant, which was 6.83 Newton meters. And the relaxed length of the spring was 1.23 meters, and the velocity was initially 0 meters per second, and the position of the weight was initially negative 0.0523 meters in the x direction, and negative 0.667 meters in the y direction, and 0 in the z direction. Experiment. To begin off, the video was attached to the spring, and the other end of the spring, the weight was attached to the spring, and the other end of the spring was attached to the fixed point, which I included in red. The professor starts off the video by dropping the weight. Then we watch as the weight swings around from the spring in an oscillating motion. Since the professor drops the spring from higher up and to the left, the spring also sways back and forth, leading to the oscillations occurring at an angle instead of directly up and down. Then, using Tracker, I got the data from auto-tracking the motion. Then, using this data, I input into my code. Included earlier in my code are the initial conditions and constants that I had discussed earlier, and I set the delta t to equal 1 over 210 seconds, which I also got from the data. First, we updated L, L hat, and S for the spring. Then we set up what each of the different types of energy were in the system. Then, in this time loop, using the momentum principle, we updated different positions' velocity, the net force, the spring components, and changes in energy. Differences and similarities. Some differences is the height of the amplitudes and when they hit their peaks, like what time. Some reasons for error. One reason could be that the professor may have accidentally added some force that wasn't accounted for in the code, which might explain why the amplitudes are taller in the experiments. Another might be that the code didn't account for the fact that the spring was swaying, which also affected the motion. Additional questions. What does this mean? Is the energy principle satisfied? As we can see in the graph, the energy principle is satisfied because delta E is 0 throughout the whole experiment. This means that although how much specific types of energy have changed, there's no change in how much total energy there is, which satisfies the energy principle that states that energy must be conserved. What does this mean? Are the periods of x and y the same or different? On a graph, to find a period, it is the difference between two peaks or troughs. So, using rough estimate from the experiment wave on the x position graph, we can see that there's a peak first at 0.5 seconds and the next one at 2.2 seconds, so the estimated period is 1.7 seconds. While for the y position graph, we see a trough at 2 seconds and the next at 3.5 seconds, so the period is 1.5 seconds. So no, the periods from the x and y positions are different, so this means it could lead into some deviations for other components in the spring. Thank you.